Okay, so I'm very excited to introduce the next speaker today, Jessica Oddan. To my knowledge, she's currently finishing up her PhD project on reconstruction from the University of Waterloo, and today she will talk about reconstructions of quantum theory, genuine explanation, and moderate realism. The floor is yours.
Thank you. Thanks, everyone, for being here. So, my dissertation project is largely trying to situate the reconstruction in some of the philosophical literature. So I'm thinking about kind of general philosophy of science, some methodology, some like philosophy of applied math, and things like that. So, all right. So we all know what reconstructions are. But there's some use in just getting kind of a bird's eye view of what some people think the intention of the program is. So reconstructions aim to uncover the unique physical features of quantum theory via axiomatization. And I'm making the argument that reconstructions offer genuine explanations that answer Wheeler's "Why the Quantum" question. And this is because they satisfy Elisa Bokulich's account of scientific explanation. So this is an account of explanation that focuses on patterns of counterfactual dependence, which capture real underlying dynamics. And these patterns of counterfactual dependence are explanatory insofar as they allow us to see differences in the explanandum if factors in the explanans are changed. And I argue that reconstructions track these patterns of counterfactual dependence within the framework when a set of axioms isolates the quantum space of theories. And the main kind of methodological machinery that enables this to happen is this framework which establishes the space of theories. So to kind of set up some of the context, I want to talk a little bit about more traditional approaches versus how I see the reconstruction program coming in. So traditional approaches tend to have an accepted mathematical formalism, as Philipp talked about yesterday, and we're taking that mathematical formalism and finding an interpretation for that formalism. So interpretation loosely is, we're trying to tell a story about things in the world. Whereas reconstructions are kind of focused in quantum foundations, and the main goal is to reformulate quantum theory from a base set of physical assumptions. So the focus really isn't on interpretation. So the focus of interpretation is kind of subverted here. And this comes out of a desire to derive the Hilbert space formalism rather than accept it at the outset. So ontology is kind of a lesser concern, as is interpretation. So it's kind of a different type of explanatory project. And I think it's helpful to try and articulate how the methodology tends to play out in this research program. So as I said, the overarching goal is to identify a set of axioms that picks quantum theory out from that landscape of theories. So we establish a landscape via some sort of framework. The GPT is an example, and this includes classical and quantum theories, as well as including superquantum theories, things like that. We then, so the idea here is that if we generate a broad enough theoretical landscape, that we're better able to pinpoint those quantum cases in that landscape. We then stipulate physically contentful principles. So these are going to be those principles that researchers take to be fundamental to quantum theory in some kind of way. These principles are given mathematical formulations where they now function as axioms. And the collection of these axioms guides us in identifying that quantum space of theories. So if we rederive the von Neumann postulates, which is the minimal accepted formalism, we've correctly found the quantum in this landscape and reformulated quantum theory. We've then shown that the postulated physical principles are compatible with and isolate quantum theory. Right, so this is in service to answer Wheeler's why the quantum question. So this question is really posed to explain why our world is described by quantum theory and not by something else. So this question really gets kind of broken down into two separate questions. And the idea is that we can only answer these questions if we're able to conceive of alternatives to quantum theory or ways that the world may have been. In this way, it's less likely that we're going to miss a potentially important formulation of quantum theory. So in the reconstruction case, the exploration of alternative formulations is kind of a shift away from thinking and focusing on interpretation and toward thinking about formulations and formalism. And I think some of the motivation for some researchers is that it's possible that there's a better formalism for quantum theory that we have not yet discovered. So how specifically do these two questions kind of like play out in the reconstruction program? I think the why this portion of that question is really a question of the origin of the quantum formalism. So we have really a well-understood formalism in quantum mechanics at this point, but the connection between the mathematical description that we have and the connection there to the world remains kind of unanswered. And this is coming from a sentiment that affixing physical interpretation to a mysterious formalism is really just not justified if it's merely heaped over and above the mathematical formalism instead of coming along all the way as it rises in a derivation of the theory. So the solution to this in the reconstruction program is to place those physically significant concepts at the outset, rather than trying to like affix them kind of at the end point. So when the quantum formalism is rederived, the formalism then will have an unambiguous origin. The why not that portion gets an interesting treatment in the reconstruction program. So optimally, an answer to the why this portion, the first portion of that question, is going to reveal what abstract physical concepts are uniquely quantum. And that's going to solidify the distinction between classical and quantum theories. So exploring the multitude of abstract physical concepts and the patterns in which they result in quantum theory requires points of contrast in order to do this. So really answering this second portion, the why not that question, necessitates alternative theories as these points of contrast. And this is where I think we really start to see the significance of the framework in terms of methodology starts to kind of enter into the story. So I'm going to use Hardy's kind of seminal 2001 paper as an example. So he situates in the GPT framework, and the GPT framework's comprehensive enough to allow for a variety of conceivable physical phenomena that's more general than those predicted by quantum theory. So as I said, we have that very, very broad space of theories. This is operational, so articulated in terms of transformation, measurement, preparation procedures. So this describes typical lab situations. Hardy chooses 5 axioms. The first 4 actually describe classical probability theory, and it's the axiom of continuity that is the uniquely quantum axiom here. So Hardy's successful. This is one reconstruction. There are many, many more now successful reconstruction. So I'm interested in what type of work reconstructions are meant to do in a kind of more general sense, and how specifically they might be explanatory. So one way of cashing this out is through Elisa Bokulich's account of scientific explanation. And so Elisa's general account of scientific explanation really focuses on how patterns of counterfactual independence can be explanatory. These patterns of counterfactual dependence are drawn from Woodward's view, which articulates explanation as providing information about patterns of counterfactual dependence between explanans and explanandum. These patterns are what he calls W questions, so what if things had been different questions. So we're kind of like thinking of it in the sense that we're trying to like track changes within the systems we're interested in looking at. And this really conveys the idea that explanation must enable us to see what sort of difference it would have made for the explanandum if the factors cited in the explanans had been changed in a variety of ways. So if we're representing some phenomena using a model, the model has to be able to reproduce the important features of the explanandum. And the model has to show us how the target system would change in response to shifting parameters within that model. So in her paper, Elisa uses the example of quantum dots. So quantum dots are devices that contain electrons within a 2-dimensional region. These are quantum mechanical systems in which it's possible for electrons to tunnel into the dot, which is typically blocked by Coulomb repulsion. And the result is that no current flows. We can, of course, increase the voltage, which overcomes this repulsion, and so we get peaks of conductance. We expect these peaks to be chaotic, in which case the wave function is, we expect to be random and uncorrelated, but that's not what we observe. So we actually see large correlations. And the explanation for this is classical periodic orbits, which is an idealized representation of the behavior of electrons. So how does this play out as it relates to patterns of counterfactual dependence in Bokulich's view? So she says that in this quantum dot case, the patterns of counterfactual dependence are captured in an equation that shows how classical periodic orbits modulate the heights of the peaks of conductance, and that really the unexpected features of this quantum dot conductance are shown to be dependent on certain features of this classical periodic orbits model. So Bokulich wants to say that this classical periodic orbits model allows physicists to answer a variety of what if things had been different questions. So physicists can now understand how these peaks in conductance might change as system parameters vary, including like the number of electrons in the dot. So she maintains that this semi-classical model is genuinely explanatory because it supplies answers to what if things have been different questions, and concludes that the classical periodic orbits are explanatory representations because they capture real features of the underlying dynamics. So there's Bakulich's example. We have a representation which captures these patterns of counterfactual dependence that accurately tracks real dynamics. Right, so how does this look in the reconstruction case? So recall that in the reconstruction case, the explanatory project is one that seeks to answer the why the quantum question. So I contend that reconstructions provide an answer to this question when a reconstruction has successfully reproduced the von Neumann postulates, designating that set of axioms as being within the quantum space of theories within that framework. And optimally by isolating a axiom that's kind of a uniquely quantum axiom. But there's an interesting difference in how what if things had been different questions play out in the quantum dot case versus how they play out in the reconstruction case. So in the quantum dot case, as I said, counterfactuals refer to different properties that a target system might possess. Whereas in the case of reconstructions, counterfactuals refer to different worlds picked out by a set of axioms within that framework. And I think what this points to is a difference in the level of generality that reconstructions are working in versus the cases that Elisa is talking about. So in the reconstruction case, we're talking about a broad landscape of theories. So we're talking about theories, whereas in the quantum dot case, we're talking about models. And in the reconstruction case, the representation is this really large framework. And of course, in the quantum dot case, the representation is the semi-classical model. So in the quantum dot case, we get explanation out of changes to those variables within the model. And so this is referencing like very specific properties and specific entities at the model level. Whereas in the reconstruction case, I think we get explanation out of changes to axioms within that superstructure. And what happens is those like different worlds are picked out within that space of theories. So what this points to is that reconstructions are really working at a much higher level of generality in a framework theory model schema than the quantum dot case, which is working at a much kind of lower level. So I contend that what's correctly captured in the reconstruction case are the patterns or relationships among regions in this space of theories. So in the quantum dot case, what's correctly captured are the underlying dynamics. But I think that this looks a little bit differently when it's applied to the reconstruction case. So a set of axioms picks out a world in the space of theories, and classical and quantum theories are going to occupy different regions. So here's where the kind of comparison comes in, because the comparison of classical and quantum regions is going to illuminate those differences between them. And by tracking the relations between different regions in this landscape, I think we're better able to understand maybe if why certain axioms are uniquely quantum, if axioms are independent from one another. And we're also able to see if more clearly if there are anomalies within this landscape that may actually give us new information. So how does this play out in Hardy? As I said, Hardy successfully reproduces the von Neumann postulates, situating his reconstruction in the quantum space of theories within this superstructure of GPTs. So this is one collection of axioms that picks out quantum in the space of theories. So it's one way of answering a what if things had been different question. It's also one way of answering a why the quantum question. So as Hardy shows, the removal of the axiom of continuity leaves us in classical probability theory, but when it's added back on, we're in the quantum space of theories again. But yes. Sorry, the first four axioms is another way of answering a what if things had been different question, but it doesn't answer the why the quantum question. And I've been thinking a lot about methodology, and as I have kind of continued to work in this reconstruction program, the significance of the framework is one of the things that I think is one of the most interesting things. So this case with Hardy is really just one example, or two examples of the types of patterns of counterfactual dependence that we might get. So different sets of axioms are going to pick out different regions within this landscape of theories. And this allows us to infer what happens when we change an axiom, where we're kind of oriented in this space of theories. And I argue that it's really this generalized framework that facilitates both the asking and answering of these what if things had been different questions. So it's methodologically very valuable, and because it licenses the inferences that track these counterfactual dependencies, so it's really integral to the explanatory value of the program. Right, so I argue that we can get genuine explanation out of reconstructions insofar as we're able to track these patterns of counterfactual dependence, the significance of which I'm drawing from Bakulich's account of scientific explanation. So reconstructions are able to provide answers to the why the quantum question when they isolate a set of axioms that situates us in the quantum space of theories within a superstructure. And particularly when they isolate an axiom that is uniquely quantum, which gives us just more information. And it's within this generalized framework that we're able to track these patterns of counterfactual dependence, so within which we can seek answers to what if things had been different questions. So the generalized framework is a very, very interesting methodological feature, which is integral to its explanatory power. So that's how I think we can potentially get a conception of explanation in this research program, broadly construed. So to kind of close off, I want to talk about some of the common questions that I've gotten from philosophers and physicists as I've talked about this work in a more kind of philosophical setting. So we end up in this space that we have a bunch of different reconstructions, and we're kind of like tinkering away in theory space. But one of the questions that I've gotten is, okay, now what? Like, so we have all these interesting reconstructions. A lot of them are very successful. So how do you tell which are the interesting ones? And I think part of what's relevant here is that interesting is going to depend, of course, on the goals of researchers, the axioms that they might use. Some researchers are going to have more pragmatic goals. Others are going to have kind of maybe some loftier ambitions. And so, like, some people think that maybe we're going to discover quantum gravity. So there's this nice quote by Hardy and Speckens. If we have a mathematical framework that's rich enough to contain a theory of quantum gravity, then we could expect that a few suitably chosen postulates would narrow us down to the right theory. It's in the construction of this framework and the selection of these postulates that the conceptual and mathematical tools of quantum foundations are likely to be successful. So, really, like, what's interesting is going to depend on what researchers' intentions are for kind of entering into this general program. But what would a potential endpoint look like? Like, where does this program end off in kind of a more generalized sense? Would it be something like novel prediction, which is kind of more situated in general philosophical literature? Like, a good theory is going to enable us to make novel predictions in some sort of way. So what would novel prediction look like in the Reconstruction program? What is it going to look like in a specifically kind of operational setting? And I think that a lot of people are excited to continue digging into super quantum relations, almost quantum relations, and I think holding those up against classical and quantum theories as we kind of generally understand them. And I think, again, this here we can see like the value of comparison, which I say is really one of the important parts of that framework. And as I've said, I think we're likely to find success getting insights, from this comparison of theories within that generalized space. So another question that people are really, thinking about interpretation, how this might hook up to an interpretation or interpretation kind of more generally. And I think part of what's important to keep in mind is that what type of explanatory project reconstructions are. It's not clear how we would get a robust ontology out of reconstructions, though that is like one of the important kind of, I think, pathways that should be looked at more. But as I've described, I think we get different types of insights from the Reconstruction program, like this distinction between classical and quantum, looking into super quantum correlations, things like that. So I think the program's really best understood as looking into the conceptual abstract structure of quantum theory. And that's really kind of one of the main intentions of the research program. So interpretation isn't really the goal, so it's not really surprising that that doesn't have an obvious kind of answer at this juncture. Like, how would we construct an interpretation out of an abstract axiomatization based on a generalized framework, where we have axioms that are kind of based on abstract physical principles? It's not obvious how we would construct an interpretation based on that. But I'm reminded of a great article by Hardy and Speckens on quantum foundations that says basically they think that success is likely to be a two-pronged approach where we have an operational side and we also have like a realist side. And that I think Reconstruction program is oriented nicely to be kind of working toward the messy middle bit between these two prongs. I also think it's helpful to think about the Reconstruction program as an instrument for inquiry. And the program generally is very like highly exploratory, and I think the methodology is suited very well for this exploratory type of project. I've also heard people talk about skepticism about operationalism. So questioning really whether, like how theory agnostic the operational formulation is, because we need background information to interpret data. So he was, thinking about like the theory-ladenness of data. But this all obviously kind of like is contrasted with the idea that operational frameworks are very helpfully neutral. So insofar as the operational frameworks are neutral, they don't contain any hidden assumptions, which may unwittingly contribute to content of theories formulated within them. And I think it's also interesting to think about the operational framework functioning as kind of like a common language with which to articulate theories and with which to compare theories, where we have kind of less of a problem with an incommensurability. But admittedly, this limits the types of theories that we're willing to consider, or kind of like the crux of what that formulation can tell us about reality in what sense, whatever sense we want to think about that. So there's lots of very, very interesting questions to be worked on in this, in like the philosophical literature specifically. And I want to tie things together by this quote by Lucian Hardy. So the way I see it in terms of this program of finding some postulates or axioms is that we're looking at some sort of strange object, and the original mathematical axioms of quantum theory give us a bunch of strange vantage points on this object. Maybe we're looking at it from odd directions. As we get better postulates, we're finding better ways to look at them. So rather than looking at it from some direction where it doesn't make sense, perhaps we should see it face on, and we see it from several different directions. So we're moving towards some more reasonable set of vantage points on the given object. So it wouldn't disturb us whether these axioms are unique or not. At least they should somehow be a sensible way of looking at that object. I think this is a really nice elucidation of how to conceive of the program, where we're seeking different vantages on quantum theory kind of as a whole. So rather than picking kind of a single perspective, which I think you can liken to building an interpretation, we can like in terms of exploration, we can look at it from a bunch of different vantage points. And I think that's what ends up happening as we construct these reconstructions. So reconstructions do a really good job of providing this exploratory space. And yeah, the methodology is really tailored to this type of project. And as it relates, kind of thinking back to these what if things had been different questions, what are these but the different vantages that Hardy talks about? Thank you.
Okay, thank you so much for this great talk. Let's start with Chris.
I love having this advantage of being the closest, because then I get it first.
First one.
Could you go back to slide 5? I was entertained by that one. So Wheeler, of course, why the quantum? And you gave Curbella and Speckin's way of formalizing that, conceive of alternatives to quantum theory, ways the world might have been. It made me think of, so Wheeler had a number of quote-unquote big questions, people call them. One of them was why existence, which, sounds so immensely broad, but Wheeler on occasion would say that when we answer the question why the quantum, we'll answer the question why existence. So I was just wondering how Wheeler would react to the Curbella and Speckin's formulation. And it also reminded me of, people often invoke Leibniz as saying that we live in the best of all possible worlds. Fewer people, and I haven't seen it too often, but some people have pointed out that Schopenhauer had the argument that we live in the worst of all possible worlds. And the argument went that if the world were any worse off, then it just simply wouldn't exist. It would go out of existence. And so, kind of combining these two thoughts that I learned from you is, since Wheeler thought that why the quantum was why existence, maybe we should be looking for a set of alternatives to quantum theory for which quantum theory is the worst of all of them. And I almost think this seriously, but so thank you for inspiring.
Yeah, thanks.
That was a very good talk.
Oh, thank you. Yeah, thanks. I wonder how Curbella and Speckins would respond to that very different kind of notion.
Can I ask one last?
Just say.
One last thing was, so you had the Speckins, I believe that was a Hardy quote.
The very last.
Yeah. That was in one of my papers.
Yes. Yeah.
That was a question I believe he asked me, or a comment he made to me at the end of one of my talks. And I think that I don't completely remember, maybe you can tell me. I think I contrasted the way Hardy was thinking about quantum theory and the way I was thinking of it at the time was Hardy saw it as this beautiful object, you could see it from many directions, and he wanted to find the point of view that sort of made it as smooth as possible, made it as less shocking. And I think I responded to him by saying, I love this metaphor. I want to find the point of view that makes it look as sharp and pointy as possible.
Right.
Did I say something?
I'm trying to, because that was the one where you're talking about like getting to the jugular of quantum theory. Is that like the same one? Yeah. I don't recall specifically. This is kind of at the very last section.
How I would answer it now anyway.
Yeah. the sharpest version possible.
Thank you.
Yeah.
So it seems that reconstructions involve a certain degree of reverse engineering, in the sense that we know what we want to derive, and people seem to choose or engineer the axioms such that we arrive at the conclusions where we want to arrive. I'm wondering if it could be argued that that's the way theory constructions in general work, because if we look at Heisenberg's construction of quantum theory, for example, he seemed to have been motivated by relying on directly observable descriptions, and also he seemed to have had in mind the selection rules that was available empirically governing the spectral lines at that time. So in a sense, he was also reverse engineering, but it seems to be a different kind of reverse engineering than in reconstruction.
Sorry, can you explain that a little bit?
Because there, he doesn't have to reconstruct quantum theory because he's constructing quantum theory. But he does have to reverse engineer the explanation for the experimentally available selection rules for the spectral lines that was available at the time. So it seems that reverse engineering operates to a smaller degree than in the reconstruction program, because there he just wants to reproduce some observable facts that just remain suspended here and there and not connected with any theory. But here, it's a different kind of reverse engineering.
Right. Okay. I see what you mean. Yeah. I think like one of the significant advantages, obviously, and this is dependent on the kind of how well developed quantum theory is at this point, obviously, right? So we have the very convenient knowledge of the kind of minimal formalism that we have to recreate. Otherwise, it really is not going to like make sense in the way that we understand quantum theory. But there's a lot of interesting things that happen kind of within. I think actually the derivation of the formalism at the end is like the least interesting part. It's really like how we play around with those generalized abstract principles and what information that is going to potentially give us. And as I said too, I think this comparison of theories and the patterns in which, okay, so we have like one reconstruction and this orients us into the quantum space. Let's remove axiom 5 and see where that kind of then orients us. Oh, we're classical, right? I think that's like very, very important information, and just in terms of trying to like navigate that space. So we have the advantage of the current state of quantum theory, which other kind of projects in reconstruction or axiomatization wouldn't have, which is why I think it's very important at this point in reconstruction or in quantum theory's history.
Okay. Hamza, you had a question?
Oh, no. Okay.
Oh, sorry.
Thank you. I have two questions. So you mentioned tracking relations among regions in the landscape of theories. Now you can have relations between quantum theories and classical theories, but you can also have relations between regions that are different axiomatizations or different reconstructions of quantum theories.
Yep.
Do you have a formal way of looking at the difference between the two?
I do not. I don't have a formal way of thinking about that. That's something that I'm thinking about right now. Is kind of, yeah. What I don't really want to do is just like place on another abstract formalism that is going to maybe not be explanatory. But I think really the best step forward would be to create some sort of like formal way of tracking these ideas, but I haven't thought necessarily about how to do that.
Yeah, if I may recommend, there's a very nice book by Elaine Landry, which is called Categories for the Working Philosopher. I think it has quite a few articles on, relating different theories category theoretically.
Perfect. Thank you.
All right, and another question, please. So if you pick certain regions and relations between these regions in the landscape of theories, do they tell you anything about ontology, or can you rule out certain ontologies based on these relations?
See, I'm not sure whether ontology is going to come in at that level, like at the kind of more. See, part of what's challenging about talking about this is there's just like so many different levels of like abstractness in the way that I'm talking about it. So I think maybe I think ontology is better going to come out of reconstructions kind of themselves, like specific reconstructions, the physical, like abstract physical principles that they're talking about, the results, and obviously there's that connection between like an operational formulation and ontology in terms of having like clear empirical information that we get from that. But I'm not sure necessarily that we're going to get ontology out of that kind of stepped back abstract relational perspective. But I wouldn't necessarily rule that out. I just haven't conceived of how to do that yet.
Thank you very much.
Thanks.
Okay, Mike.
Thanks. I'm just wondering, so on one of your slides, maybe about halfway through, you mentioned something about whether a reconstruction is interesting depends on the interest of the researchers involved. Right? I think that sounds right. But I'm wondering if you had any thoughts or opinions on, not so much on whether particular reconstruction is interesting, but whether it's more likely to be successful, like whether, like for which research programs, do you have any thoughts or anything on which kinds of reconstructions would be more likely to yield insight as opposed to ones that are more of a dead end?
Ah, interesting. I haven't thought about that in particular. I'm kind of an equal opportunist here, like kind of like go as you will in terms of like I think that's one of the main points here, and one of the main advantages is like this is a really highly exploratory program. It's a really highly exploratory methodology. So I think like yeah, that's one of the main advantages. So no, I don't have any specific like yes, I think this program is going to be more successful than others. I think that it's going to take more time, but success is going to look different also depending on your goals, right? Success might look like more practical kind of advances in technology. Success might look like, okay, now I'm thinking about indefinite causal structure, and that's going to like create a whole bunch of other, theories or things kind of down the road. So no, I don't have specific kind of versions or ways of like in reconstructions that I think are likely to be successful. And I would be hesitant to suggest that anyone not pursue certain directions.
Julian? Okay, thanks very much. This is a very nice talk. I have a question about counterfactual dependence, but first I have a couple of suggestions. So, I think I heard you talk about reconstruction program as a research program, right? And to a philosopher of science, that immediately, sounds like Lakatosh, right?
Yeah.
So I think it would be very interesting to, see if a case can be made for the idea that the reconstruction program is something like a Lakatoshian research program. Lakatosh, of course, being one who talked extensively, investigated extensively reconstructions in the history of science.
Right.
So maybe there's a connection there. Secondly, I think I heard you say that reconstructions are mostly interested in uncovering the origin of the standard formalism. So, I'm not sure. I mean,
Fair.
maybe some of them are, maybe some others are more interested in, justification of the standard axioms. So maybe that needs, some more analysis. Question.
Yeah.
Right. So this is a question about the appropriateness of applying Alisa-Bakolich's analysis, understanding of explanation to the reconstruction case. You mentioned that there is a distinction between the two cases, right? In the case of quantum dots, what you change, right, are the facts about a certain system,
Yep.
right, properties of a certain system. In the case of axioms, you don't really do that unless you take axioms to be some kind of facts, right? So maybe, unless you say more, that counterfactual dependence looks more like a counter-axiomatical dependence to me. I'm not sure how to understand that, but...
Counter-axiomatical dependence, that's an interesting one. Yes, so this is a very good point. I've heard this as well, right? Like, okay, so these cases are different, so doesn't that undercut explanation in the reconstruction case? And I have thought about that, and I think that I can still, like, the main feature that I'm really interested in is the counterfactual dependence, because I think that very nicely captures what happens in the landscape. And you are absolutely correct that changing an axiom within a reconstruction is not the same as changing the number of electrons in kind of Elisa Bakolich's example. And yeah, that's why I did point out the difference, but I don't think that, I think I can, that's talking about like Woodward's kind of interventionist manipulationist kind of perspective. And Elisa does not want to conceive of her case study in the interventionist or manipulationist way either, because she doesn't want it to be causal. So she has other work talking about how to get explanation out of like non-causal. But I still think that the significance of counterfactuals is applicable even in the Reconstruction case, where it is a much more abstract level. I think in principle, there's no reason that we can't get that same importance of counterfactual dependencies at this higher level of abstraction and reconstructions. Changing an axiom isn't an intervention in the way that changing something in a model is, but I think we can I still have to kind of like fine tune this, but I think we can still take some of the crux of the value of that type of explanation. Yeah.
Marty, you have a question?
Thank you for this clean presentation with clear topics and in a very well-organized manner. Thanks. My question is exactly about the role of counterfactuals in explaining the project of reconstructing quantum mechanics. What I wonder about is exactly what do you mean by counterfactuals and its relationship with the reconstruction program, because it seems to me that this program is not cannot be explained with counterfactual, but by actual if-then conditions. At least, for example, about reconstructing a special relativity, which usually mentioned in the beginning of discussions about reconstructing quantum mechanics. The way to reconstruct the special relativity is not to say that this is a counterfactual way of reconstructing that, but to say that if we have two principles, actually we can construct that theory. So in counterfactuals, we do not have the actual condition. For example, we can say that if we were not here in this room would be empty. So this is a kind of counterfactual. So it is not actual. And in reconstructing quantum mechanics, I think that a version of actual if-then conditions is used. People say that we can actually reconstruct quantum mechanics differently if we have two different, for example, 2 or 3 other principles. We can actually reconstruct quantum mechanics. So it's not a kind of counterfactual way of reconstructing its actual if-then conditions.
Yeah, thank you. Yeah. So I think part of why, I definitely take your point. And I'll have to think about that more. Part of why I think counterfactuals are helpful is when we think of reconstructions as representations. So what is meant by actual in these cases, when we're talking about an abstract generalization, I'm not really sure of how to determine what is actual when we kind of derive a base formalism. So I'm interested in keeping the reconstruction program in some senses in this more abstract representational view, while not necessarily talking about actuality. And that's why I think counterfactuals work nicely to kind of indicate to us where we're not getting successful reconstructions. So that's my first kind of thought at your question, but I will definitely think about that more. Thank you.
Okay, could you move one slide back? I think this slide number 21.
Yeah.
Maybe it's slide number 20. Yeah, this one. Okay, so here you talk about the relationship, right, between reconstruction and interpretation. You point out that it's unlikely to expect that we can, like, the interpretation like emerges straightforwardly from reconstructions, right, if I understand you correctly. And then you say in the penultimate point, how do you construct an interpretation out of an abstract axiomatization of a theory based on a generalized framework and abstract physical principles? Do you here describe a situation after you've reconstructed quantum mechanics? Or
Sorry,
do
what?
you describe here a situation after you have successfully reconstructed quantum mechanics, or the situation before you have reconstructed quantum mechanics?
After.
After.
Yeah.
Because typically, reconstruction people, right, they would say that the principles that we are looking for should not be too abstract. Say something like crisp physical principles, say something like intuitive physical principles. Of course, it's the goal, right? Don't say that the actual reconstructions that we are familiar with provide us with this super clear framework. But this would be the goal, right? So I was a bit surprised that you would emphasize this abstract 2 times in this one sentence when you describe the situation after you've reconstructed. But, I mean, maybe you want to say something like this. What comes to it?
Right. Yeah. I guess I'm kind of trying to push back on the people that I've talked to who are like concerned only with interpretation all the time, and like whatever is happening in other like projects, if you don't have an interpretation, like I'm really not that interested in it. And I think, that's not a great viewpoint to have, because there's a lot of value in other types of things. But I think it is important to recognize how abstract the reconstruction program is. There are certainly ties to it's not super like high up in the clouds to the point where we're just like navel gazing, but it's definitely more abstract. And I think that's important to consider when people are asking, okay, so if you don't have an interpretation, then I'm not really interested.
Right. Wonderful. So thanks again for this great talk. So Lucy.